rights granted by GOI. He has also completed a research project sponsored by Royal Society UK in collaboration with University of Bath UK in NIT Jalandhar between 2019 and 2022. He has also developed some specific impact testing laboratory, very much improved by the Senate. And he also has organized some international conferences, national conferences before this, sponsored by TechU. He is recipient of the Best Teacher Awards at NIT Jalandhar in the year 2018-19. And beside that, he also have got several awards for excellence, including 7 national awards and international awards. He is also a member of more than 10 civil engineering society, including fellow member of Indian Concrete Institute and Indian Geotechnical Society. So with this very short description of yours, I come to this platform.
Yeah, I'm not actually sorry to say I'm not a fellow member of Indian Geotechnical Society, but I'm fellow member of Institution of Engineers, IEI, Indian Institution of Engineers. Yeah, I'm sorry. Yeah.
Okay. No problem, sir.
Yeah, thank you. Thank you very much for the brief introduction, sir. Thank you very much. And first of all, I'd like to thank the IGS Shimla chapter, and also the special thanks to Dr. Amardeep Bura. He's my close friend, and also we were doing PhD together in IIT Roorkee. And also today, it's a great honor that Professor Samadhi sir also attending this lecture. So, sir, I'm sorry, it's like it's a very, very good presentation, but I hope you'll enjoy it, and I hope everyone will enjoy it. So, the talk is specifically the response of the reinforced concrete tunnels under repeated loading. Maybe it's varying drop height. So that's what is a main importance of this presentation. Basically, I was not working in the tunnels since 2018, but 2018 I have submitted one proposals to the Royal Society UK with collaboration with University of Bath UK and NIT Jalandhar. So we got that project, but that project is purely for mitigation strategies on this underground tunnels against blast loading. But as an educational institute, we cannot perform any blast type of experiments. So then we decided we will go with the impact studies. Then we will extend to numerically we can do it blast loading. That's what we did. And we got in the year 2019 those project, and then it was completed 2022. And mostly all the results were published, and like maybe 3 to 4 papers and a couple of papers in the Impact Engineering Journal, also International Journal of Impact Engineering, and also International Journal of Protective Structures. With this brief, maybe I would like to highlight in this particular presentation, I discuss about some very general terms, and then some of the experiments, how we perform the experiments, and later some of the modeling techniques we have used, especially the abacus finite element modeling, and then some of the parametric studies that we have carried out. So before maybe going to the underground tunnels, of course, previously we have many mythologies. Okay. So the experiments specifically we carried out maybe since 2000 or maybe before 1980, the things were different. We have to study through the comprehensive experiments or some basic experiments, then we have to understand. But it is quite costly. It's time consuming, costly, and also the precise test settings and including instrumentation is very, very essential. So the modern technology, especially after 2000, maybe I can say I completed my 10th class in 99, and then I took a computer science because I felt I want to use some modern technology. So in my 11th and 12th class I took computer science. So this computer programming actually it's coming up maybe after 95 or 90. Before that it's a bit lag, and the technology is not that great. So the theorem also actually, especially the plasticity and molecular dynamics and all, actually it's coming up and developed maybe after 1980 or 1990, especially this elasticity and the plasticity, large deformation problems. So since 2000, the finite element analysis is one of the one of the good techniques, numerical techniques actually come into the pictures, and especially to cut the prices or the cost of the experiments, and also the quickly we can achieve some results maybe. But yes, we have to put a lot of effort. That's one thing. So this present study is focused to demonstrate the accuracy and the effectiveness of the finite element based models, and to study the structural behavior of tunnels using the commercial finite element methods. It is a prime fact of this presentation. So the tunnels, why it is coming? Because of rapid urbanizations, the city development and horizontal expansion rather than the vertical expansion. So this is the one reasons actually, the tunnels actually coming up. The tunnels plays an important role, especially wherever the blockage we have. Suppose if you see, I think especially in the Himachal Pradesh or in even the JNK, there's two states. There are a lot of obstacles topographically, like mountains, rivers, falls, valleys. So this is one of the things. So the tunnel is important part, and we need tunnels. And need of construction of tunnel to provide better connectivity, of course. Maybe 10-15 years before even going to Kulu or Lagul or Manali, it takes several hours. Now, for example, Kulu also we can reach from maybe Jalandhar to Kulu hardly 5.5 hours we can reach. So earlier it takes 10 hours plus, and again the Manali takes another another 3 hours, 2 hours. So but we have a lot of advantage because of this tunnels and other facilities. But at the same time, the problem it starts with the rock fall, the rolling and falling of the rocks, and our sudden accidents. But maybe it's a very rarely takes place. But if it happens, so how to protect? So what is the damage, and how this damage to be assessed? That's what is covered in this presentation. So the tunnels, especially in India, we have almost 4,000-kilometer tunnels. What I feel, if I'm right, maybe it's more than 4,000, but 4,000 tunnels approximately, I can say. And both railway and road tunnels, especially this few tunnels which having a span about 12 kilometer, 12 to 9 to 12 kilometer approximately. That is was the highest or longest tunnels in India, especially that covers in HP or Srinagar, Jammu, JNK. These two states have the longest tunnels, both the railway and highway applications, including the Kerala. Some of the tunnels, it's the longest tunnels we have. And also now in future, maybe it is expected, the longest tunnels maybe coming into the pictures. So what we did, we have casted the tunnels. We have considered the semicircular in shapes so that easy to construct. Okay. So and the length we have considered the reduced scale, roughly it's a scale about 20 we have considered. So 1.2 meter length tunnels we have made, considering the internal diameter of 0.5 meter and the
Uh,
thickness of the.
Dr. Senthil, sorry to interrupt, but slides are not changing actually.
Oh, sorry. Which slide? Slide number 6 is not visible.
Uh, Now it is visible, but it is still not in the presentation mode.
Oh, okay. Then I will share maybe. Can I share the entire screen or
Yeah,
window?
that will work. The entire screen option.
Entire screen. Can you see the screen, sir? Now, full screen mode, presentation
Yes.
mode.
Now it
Yes,
is
sir. Yes.
visible properly.
Yes, thank you, sir. Yeah.
Thank you.
So the tunnels we have considered the length, it is a 1.2 meter with the internal diameter of 0.5 meter, and the thickness of the lining we have taken it's 50 millimeter. Okay, we have casted with RCC tunnels, and of course we have used the instrumentation, very sophisticated instrumentations. We have tried to extract the significant informations, and these experiments were performed by the drop impact test, and considering the mass of the impactor about 100 kilogram, and also tested under different heights, like a drop height as 1.5 meter, 2.3, and also 3 meter height we have tested. And further, these experiments were validated using the finite element software. And further, we have studied the parametric studies, because such a small tunnels, it is just a laboratory, it is possible. But when we go for actual tunnel, it may be the case different. The length, the span is different, and the length is different. So that's what we have varied, and we have studied how the response actually due to increasing the drop height or increasing the span, how it takes place for this corresponding this 100 kilogram of mass. Of course, we have not gone to such a detailed varying the mass or varying the thickness of the lining. That much we have not studied, but because the scope of the projects, we have satisfied, and considering the two parameters like a length and the diameter of the tunnel, then we have studied. Mm. So these tunnels, the reinforcements, we have used 6 millimeter bars, and placed at a 60 millimeter spacing, and the tensile strength, yield stress of these bars are 450 MPa. And then the strain gauges were used in the reinforcements, so that to measure the the strains. This is one of the important part of these things, because whatever experiments you are performing, the retrieval of the data is a very, very important. So where you are placing your strain gauges, and what kind of instrumentation you are using, and how this data is retrieved, which data logger is used, it's a very, very important. And so the sophisticated equipment is very essential. And further, because the strain data we have to retrieve, okay, so that is one of the important things. So we have to take such a way the very sophisticated data loggers, maybe it's the frequency about at least 10,000 heads, or sometimes more than that also, that if the data logger carrying capacity, its sampling rate especially should be very high. So the tunnel was supported with the soil base. That's what is the right side figure you can see. The tunnels were made, and just a simple assembly we have shown in this slide. And also these tunnels were cured. Okay, the whatever the material we have considered. Briefly, I have given the materials, like we have proposed it's I think M25 grade concrete. M25 grade concrete. Sir, the slide is visible, right? Now it is not a problem.
Yes, yes, it is
Right.
okay now.
So M25 grade concrete we have considered, it is because it's a simple to cast, and mainly it should be workable, because it's like the standing position we have casted because of complexity in the shapes. So it's a 1.2 meter concrete we have to pour it. We have to pour at a height of 1.2 meter. So there is a possibility for the segregation and other characteristics. So that's why we have taken simple M25 grade concrete, and to avoid the complexity in the vibrations or requirement of the vibrations or honeycomb, etc. And further, we have cured as it is, and the mixed design and other things we have taken care as per IS code. And this test, this particular testing frame, we have fabricated in front of Civil Engineering Department, NIT Jalandhar. And this is a very simple test setup. And this mass we have even this particular mass also we have defined, by different trial and error. Initially, we have made only the steel balls. It's about 1 feet diameter steel balls. So if it falls over because it's an effect of the rock we want to develop. So we made the steel balls, and we have tested, but again, the varying height and other things, the many issues actually came up. So then we made such a way, there is a hemispherical nose that we placed around 100 height, and a diameter about 75-80 millimeter diameter, hemispherical diameter of the impactor nose that we have used. And the bottom two plates and also top one plate we have used. And actually, initially we planned to use load cell also at the bottom in between two plates, so that the load cell will be mounted in between the two plates, so that a load cell will give you the impact force. But again, the sensitivity of the equipments, because there are high chance the load cell and the wire may get damaged during the free fall. So that's why we have not placed the load cell. The load cell, or you can say the impact force, were recorded using a simple principle of energy principles. Nothing else we have used. So the heavy spherical radius of 40 millimeter diameter nose we have used, and the height is about 40 millimeter. And now let's move to the some of the figure. So the some of the videos. Okay. Now this is the simple the tunnel. It is actually without any soil we have tested. Okay, this is the tunnel. So you can see after a heat, the impactor actually it's a falling. So if it is a load cell, of course there are chances that anytime it may which direction it goes we don't know, so it may get damaged. So that's why the load cell, also the connectivity, it may get damaged, so we have not used load cell. And this is actually that's the first hit, that means just at the beginning of the test. And then we have went to the second heat, that is a multiple heat. So the second heat also we have tried with a height of 3 meter drops. So how actually it takes place? So if you look at even suppose if we drops the steel ball alone, there is a uh, there is a chance that only the local impact will develop. But when we use this particular plates, especially the steel plates, that steel plate try to give you as good as that cause global impact. So because when the rolling of rocks takes place, when the rolling or whatever rocks takes place, rocks hits the structure repeatedly, it may not be it's the same shapes, it may not be the similar in nature. It may be some big rocks or maybe some small stones. Mixer may it is a possibility for mix mode. So that's why we have used this type of arrangements also, that we have, by the trials we have arranged, we have changed. Now let's go to the tunnels with soils. We have filled only around I think 150 millimeter filling we have considered, because we couldn't go, because what will happen if we fill more, because the nose height is only 40 to 50 millimeter, near about 100 millimeter, not more than that. So if we fill it more, then the soil itself takes the entire load, and it will not reach the tunnel. So that's why we have filled a very nominal soil filling. It's about 150 millimeter. Then we have tested, and suppose if you see here, this is the first heat. And this is the multiple heat. It's like a second heat, a third heat. So you can see how this tunnel actually, the concrete tunnel, it deforms, and the response at the base, how it takes. So all this we can see. Okay, and further the response were recorded in the form of the residual displacement, residual scapping. So all this we have recorded. And this is the first heat. So what is happening, we can see this is a like a before impact and after impact, and you can see there is a very small cracks. But when you go to the second heat, you can see it's a significantly wide cracks at the crown. Okay, and also there is a compression damage. You can see at the top surface there is a compression damage, and of course the tensile damage at the bottom of the tunnels. And the strains we have recorded, but some of the strain cages were not actually, I think 2 or 4 strain cages we have used. I guess I think 2 to 4 strain cages we have used, but couple of strain gauges were not giving any readings. So we should, whenever we go for testing, you try to always go for more number of strain gauges or accelerometer, whatever we are placing it, so that you will get a good number of results and we can use it for the validation. And now let's go to the third heat and fourth heat. The third heat, you can see there is a significant damage at the top. That is a compression damage. And at fourth heat, you can see very clear, this is inside the tunnel. You can see that's a significant scapping of the concrete. And also there is a, longitudinal crack in the tunnels. Okay. And further, this is the test actually at 1.5 meter height. Okay. Now let's increase the height. Suppose 2.3 meter height. So what is happening at the first heat itself? You can see the longitudinal crack. It's a very precise crack that developed, and of course it's a very insignificant compression damage. So there is only tension damage that is very particular. And then the second, third, fourth heat, you can see it's a significant damage, and especially at the fourth heat at 2.3 meter, there is a significant loss, or you can say the scapping and damage at the top surface of the concrete. And further, this is a result at a 3 meter drop height. So at 3 meter, what is happening? In the first hit itself, there is a significant crack. Even diagonally, there is a crack. Also longitudinally, there is a crack. You can see inside this particular right side picture, the top right corner picture. You can see that is inside the tunnel. The cracks were actually both longitudinally. Also, there is a diagonal cracks. And now, if you go to the second and the third hit, you can see, second hit. Just you see this picture, what is happening in case of second heat, the first heat and the second heat. First heat there is only cracks. The second heat there is significant damage or scapping. The volume of the concrete significantly it's gone, or it just exploded. And further we went to numerical simulation. So this is the behavior we want to capture. So the impact force we have, the strain we have for the validation, also the residual displacement we have. These three data were used for the validation. And the geometry of the concrete tunnel as well as the soil and the reinforcement were modeled and considered as a deformable body, whereas the impactor modeled as a rigid body. The concrete we have considered as M25, as already told you. The steel reinforcement near about 420 MPa strength were considered. And dynamic explicit analysis we have considered, and the time step is 0.05 seconds. And the frequency kept, it's time step near about delta t, it is 1/100.
Sir, if we change the section from circular to oval, then what would be the difference?
Sorry.
So like we are having the tunnel section, we are having them as circular section or oval section.
Actually, disturbance is lag raha hai. Can you please repeat?
Sir, the tunnel sections which we are testing are oval sections or circular sections?
Amandeep sir, or somebody else, can you help me? What is
He's
saying?
actually he's asking that the tunnels which we are testing are actually the oval sections or the circular sections.
No, it is circular. It is circular, sir.
It's circular only. Arman, we can take the queries towards the end of the lecture in the discussion session. I think we can
But it
first finish the
is a
lecture.
circular section. It's not a problem, sir. Maybe anyone can interrupt. It's not a problem, sir. It is not a problem, Atash.
Okay, sir. Okay.
Yeah. Okay. So the time step we have considered 0.05 seconds, and the frequency we have considered, or you can say the delta t is 1/100 seconds. Sir, can you hear me?
Sir, yes, now you're audible.
Yeah, yes. My presentation is visible.
No, sir, no, sir. No, yes, it's come.
Sir, can you hear me?
Yes, yes, yes. Now it's visible, sir.
Sir, can you?
Yes, I can hear you, sir. Your presentation is also visible.
Okay. Can you hear me, sir?
Yes, sir. We can hear you.
Done. Thank you, sir. So the concrete was considered as a host. Right. Thank you very much, sir. Yeah, the concrete was considered as a host zone, whereas the steel was, you know, right, sir. Sir, I think the voice is reaching late.
Yes, I think there is some lag. I think you can continue without interruption. That will be okay to us.
Sir, now can you hear me? It's a very proper.
Yes, sir.
Yes, sir. Done. Thank you. Yeah, and also the surface to surface contact between the tunnels, surface contact were considered between the tunnel and 8 node linear brick elements for the concrete, and were considered. A lot of trial and errors. Also some assumptions we have the computational so the depth that we have done, that like a dimension of the soil samples were taken as 1.83 meter by 1.2 meter, and the thickness were considered 0.3 meter. Okay, but actually to understand the depth of the soil, at what depth this soil pressure goes, for that you have to use some theoretical equations. There is a equations, and based on that equations you have to derive this pressure distributions. So accordingly you have to choose the soil dimensions. This is the one thing. But here, here maybe that we have not followed because of some of the constraints. So that is one thing I want to highlight here. And the reinforcement, as you told earlier, that we have modeled, and this is an assembled model that you can see top right corner, both soil tunnel inside the tunnel lining there is a reinforcement, including the with the impactor. And this is the very precise model. We are considering the boundary conditions at the base. We have considered because at one point the soil may not deform, right? So that's what at a 0.3 meter we assumed it. There is no deformations because the force is hardly 104 kilogram, which is acting over the order. So that's why we have considered very less element meshing. The meshing was varied for the concrete, so that in the mesh sensitivity, that is very important. Okay, we have to do the mesh sensitivity analysis.
Participants, please stay tuned till our speaker are going to rejoin.
Sir, can you hear me?
Yes, sir. Yes, sir. We can hear you.
Oh, this particular slide is not, you have not listened.
No, sir. No, not
This
this one.
slide,
No, sir.
okay. This slide,
Yes, you were
uh,
discussing this one.
okay. I think I don't know the network. It dropped out. Sorry.
Okay.
So this is the complete arrangements of this model and with the boundary conditions. And now let's go to the mesh convergence. And we have considered the mesh size. The different mesh size, let's say 20, 15, I think 10 and 7.5. These four mesh sizes we have considered for the concrete. And otherwise, the mesh size for the soil and the steel reinforcement that we kept constant. But one can do a detailed mesh convergence study also if you are actually interested. Uh, that is just for information. So the choice of the constitutive model is a very important. Suppose, for example, the soil, we have a different models. Even if you go to the Abacus library or ANSYS library, you have a different models. So which model you have to choose? For example, I'll tell you, uh, we have studied the response of the brick walls, okay, clay brick walls. The bricks we have modeled using the Dragerberg model. Also, we have modeled bricks using Morkulo model. And the same model, and some extent Morkulo model was giving better result than Dragerberger model. So, but in this case, tunnel problems, we felt a Dragerberger model is giving better results. So that's why the choice is very important. So whether you have to choose a phenomenological model or physical based model. As a civil engineer, we can limit with the anyone. It's not a problem. And now a few constitutive models I can say just for your information. So for a phenomenological model, we can say Johnson-Hook model and or KHL model or Arrhenius type model. And also the physical based models, the Armstrong model is one of the very, it's a renowned models. And if you go very specific for metals, soil, concrete, ceramic, we have very specific models. And because it depends on sometime whether the material is a ductile or brittle um, or it is something else. So that all we have to decide and we can choose it accordingly. Now, for Johnson-Hook model, for especially for a steel reinforcement for metals and ductile material, we can use. And these parameters actually during my PhD I have characterized and used. And maybe if you Google it, you will get idea and more widely used. It's generally available in the Google. You can go through these models. And for four different metals, actually, I have characterized during my PhD. So I don't want to just waste my time, presenting here. Or maybe you just, if you have any queries in this regard, you please contact me, not a problem. And this is the parameters that we have used for the steel reinforcement, considering both strain rate, stress state, and temperature effect under strength as well as a failure state. So all this, because mainly the strength is nothing but the model. It carries the load. When it reaches the maximum or ultimate load, your strength model kadam ho jayega. There is no effect. Then it is called failure model. Okay, after reaching ultimate point, whatever the behavior that we can consider as failure. So because your strength is, or you can say your displacement or the resistance or the forces start decreasing, so that is called a failure model. So both this thing A, B, C, N, M, it is strength constants, and D1, D2, D3, D4, D5, it is actually failure constants. So for concrete, this concrete damage plasticity, one of the renowned models that you can use. It's simply compressive behavior and tensile behavior. And for a soil, we can use Drager-Bergel. As I already told you, you can use even the more cooler models for there are standard material constants. Either you can calibrate those constants through the characterization, or you can take it from the literature. It's the best if you're characterizing those material parameters. It is always good because that will try to give you the realistic results. And the mesh convergence, as I already told you, we have carried out by varying the, we carried out mesh size, mesh sensitivity analysis by varying the mesh size 20, 15, 12, and 10 and 7.5 mm. Okay. So what displacement actually we got from the experiment, it is about 32 millimeter. That is what is called residual displacement. Also the corresponding impact force about 95 kilonewton that we have achieved when the element size in the concrete about 7.5 means about 10 to 7.5 millimeter mesh size. So that mesh size we are considered for the further analysis. And this is the simple, three different cases of drop height when it is 1.5. What is the downward displacement, and 2.3, and also 3-meter height. So the 3-meter height actually drop impact test experiments were actually validated, and that's what is the results previously we have shown. And also the strains we have recorded, the strain experimentally we got micro strains about 150, 175 from the experiments. So the numerical strain also, which is reaching about 185 or 190 micro strains that we have achieved with maybe maximum deviation of 10%. However, the experiments immediately it comes down. Maybe the strain gauge, the response, you can say. That's why sometimes what happened, especially recently, I came to know I'm using some product, some machinery, some equipment which I purchased from the applied measurements. But HBK suggesting different. You have to use for especially the strain. We have to use very sensitive machines. So maybe I can recommend because my equipment is not capturing the strains. Okay, that I have purchased from the applied measurements UK. But if you are buying a HPK, because HPK is also one of the renowned manufacturer, the data logger and including the devices. So that may be a better whatever the conversation I came to know, because I was not happy with these strains which I got. But anyway, this is just for your information. And otherwise, this validation is actually not okay. 10% deviation, it is acceptable. However, it is not not that satisfactory, because the flat to effect which is happening in the numerical results, whereas in the experiments there is a no flat to, directly it's a flat. Okay, there is no flat to effect. And these are the different failure patterns under 1.5 meter, 2.3 meter drop height, also the 3-meter drop height, and that we have compared, and also the residual displacement also just compared. Now what is happening, the compression damage, the damage C describes compression damage, damage T describes tension damage. That C and T, it is nothing but the compression and tension. So what is happening in the front side, like a 1.5 meter and 2.3 meter and 3 meter. So front side and rear side, and that we can see from this image. And similarly at maybe if you recollect the experimental results, we can get this idea how this actually the cracks develops. Also some of the videos that maybe I can show you. So during impact, because we don't know actually what is happening. Okay, if you when you drop the slow motion videos we have recorded, and yes, we can try to get some inputs. But if you carry out the finite element analysis, definitely you will get more insights. That's one of the main advantage of doing this, such a comprehensive numerical analysis. Okay, and this is the displacement. How the displacement you can, it's how it is happening. It's almost 46 millimeter displacement. That's what is happening. And here, if you see the damage, how it takes place, how the damage is propagating. Can you see the video, sir?
No, sir, not still.
Acha. No, this tension damage video is not visible.
No, sir, no, sir, not as of now.
Oh, it is too much lagging. Even the displacement video is not visible. I was playing the displacement video. That means my screen and my voice, there is a lag.
Sir, earlier that was visible, not as of now.
Okay. Now I'm repeating again this tension damage video. Can you see this now?
Yes.
Okay. So you can see there is a significant crack that develops, when the 3-meter drop height actually takes place. So that we can see very precisely those cracks, and also some a little bit of spalling at the edges, so that we can see from these images. So this is just for your idea, so that you can further use the techniques, and you can get more insights. And so what is happening in the displacement, that I can tell you, when you have 1.5-meter drop height on the hit 1, hit 2, hit 3, hit 4, hit 5, up to fifth hit we have seen, and the displacement is of course increasing, and at fifth hit we have reached 60 millimeter. But when the drop height goes to 2.3-meter, we are going up to around 100 millimeter displacement. When the drop height increases to 3-meter, of course it went up to fourth hit. So the simulation shows about 120 millimeter displacement, so quite high. And this is the simple comparisons, how this forces actually, how this forces, it's a varying. Suppose 1.5-meter drop height, your force is keep varying. At one point, of course, at a fifth hit it is it's not increasing, as it's a slightly increasing. And when you go to the 2.3-meter height, it is almost to fifth hit. The material lost their strength. There is no resistance. There is nothing to offer much resistance. When you go to 3-meter height, also at fourth hit, and the material may be lost their complete stiffness. So 132 kilonewton, it is a maximum. That's what we have achieved from the numerical simulation. And this is the acceleration. So we cannot we have not used in our experiments the acceleration accelerometers. So but this thing we have achieved from the simulation. So of course your force is increasing, that means your acceleration also it's increasing. So from maybe 600 to almost 1200 newton, that means 120 g maybe we are reaching. And then for 2.3-meter height also, we are reaching about 1400 newton per second square we are reaching. And when it is a 3-meter height, it's of course second heat, it is reaching about 1500 newton per second square, and thereafter it is decreasing. So only second heat it gives highest resistance. So that means on the material lost at the second heat itself, so there is a less increase in the resistance. And further, the tension damages that we have compared on different cases. for both, heat 1, heat 2, heat 3, and heat 4, and all different cases. Further, I'd like to go maybe the different, parametric studies, because the multi-heat impact, that is fine. I don't want to discuss further. So the length of the tunnel when you vary. So what is happening? This is the 1.2 meter length, which is actually equivalent to the experiments. It's near about 30 millimeter displacements that we have achieved. When you go to 3 meter, this is a 3 meter length tunnel. Sorry, it's a 3 meter, 4 meter, and 5 meter. These three cases we have studied through simulations. Of course, the displacement is decreasing as 3 meter and 4 meter, 5 meter. When you go length, the displacement is significantly reducing, maybe 15 millimeter to 10 millimeter. So that means there is a local effect. There is a local failure due to this impact. There is no global failure. So maybe due to this rockfall impact, even the multiple hit happening, it may not affect your tunnel. That's what the simulation actually stating. This results maybe further you can validate, if we can verify by performing more simulations, and maybe by doing some case studies. Okay, this is some insights for you people. And the acceleration which I have recorded, yes, it is a constant. After 1.2 meter, the acceleration is a constant. It is nothing changing, irrespective of the length of the tunnel, either 3 meter or 5 meter. The acceleration is about 100 g. Okay. Now let's talk about the damages. By varying the length, you can see that the damage is only local damage. Even you go increase the length, it won't affect, because at maximum 1.5 meter length, or maybe the shorter span length tunnels, it may be sensitive. That's what I want to say from this simulation, based on the findings from this simulation. Next, we have varied the diameter of the tunnels. So by varying the diameter, there is a increase in displacement that we have noticed. So 0.5 to 2 meter when we are varying, 0.5 is actual our experiment, 2 meter is a numerical simulation. So displacement is increasing significantly, near about 140 millimeter. Of course, here your acceleration that actually changes, and the damage also, it is when the diameter increases, of course, there is a damage change. Otherwise, it's a local damages, but a compression damage a little bit it is there. Otherwise, it's a local damage. So let's conclude this presentation. In case of length variation, the impact force remains, maybe it's a constant. You vary the length, it won't affect your response. And the optimum damage the optimum damage area has been observed simulation is a 1 meter diameter. And so the sir, can you hear me?
Yes, sir. Now we can hear you. There was some disturbance in between. Slight
Okay, yeah,
disturbance
yes,
while
sir.
in the conclusion slide. Yeah.
Acha, there was disturbances.
Yeah.
Yeah, can you hear me now?
Yes, yes, yes.
Acha, here there was a disturbances.
Yes. There you got disconnected for a while. Your voice got disconnected for a while.
Okay. Actually, maybe some phone calls. That's why. Actually, I'm using the internet from the mobile, because the institute internet just disconnected due to some power shutdown.
Okay, okay,
So
okay.
yeah, As the dimension, especially length and diameter of the tunnel increases, the damage is confined near the impact area. Of course, the damage is not, affected or increased as either increasing length of the tunnel or increasing diameter of the tunnel. That's what is the conclusion. So the local effect is significant. Local failure is significant. So with this, I would like to conclude my presentation, and yes, it's open for the question and answer.
First of all, I'd like to extend my thank to you for coming to this platform.
Yes, sir.
Sir, thank you very much for this wonderful presentation. And
Thank you very much, sir.
some queries are from my side first. I would like to ask you some like questions which I'm getting into my mind. First question, sir. Maybe I missed initial few slides earlier because I was in some meeting. Okay. So I want to ask you, sir, that this uh, study was conducted on the like uh, this tunnel based like fully loaded means that was the loaded with the soil mass or with the some water charge will be over there.
Hmm. No, yes, we actually, what happened, those experiments we have performed, but the buried tunnel, what we have shown, maybe the second video, this video, this simulation I have not presented over here. I have presented only the simulation of these results. The buried tunnel results I have not presented.
Okay, fine, fine.
Hmm.
Okay, so this tunnel was which was buried into the soil mass. Those you were tests were conducted on those only,
Yeah, exactly, sir.
not for the water was flowing between the this kind of tunnel because the circular tunnel mostly we are supposed to utilize for the water bodies, na?
Yeah, yes, sir. Maybe that may be, more realistic case I can understand. But what happened at a experimental level? Maybe we have to go for some other bigger level. Maybe then because what happened? Maybe when you drop with water or the soil with saturated soil, this is as good as saturated soil. So
Right.
fully compacted.
Right, sir. Right.
It is we tried a good compaction and we did.
Okay. Right, sir. Right, sir.
But however,
And,
with the water, maybe if we are dropping it,
mhm.
I don't know. I don't know that cause any impact at a experiment level, but maybe that will be like a future scope.
Right, sir. Right.
Sir, can you hear me?
Yes, I can hear you, sir.
Sir, can you?
Yes, sir. Your voice is
Right.
very clear to me.
Mhm.
Yes, sir. Another request is from my side
Yes.
that you did some simulation, na, sir. So maybe that will be more beneficial to
Yes, sir.
the like reviewers or which are joined already over here in the this presentation. If you let them or let us know that the what are the colors meaning over there means we are not able to get with the crackings because we are not doing this kind of simulation. So if you may just let us know that
Okay.
this color is meaning to this if this is getting like this.
Okay. The damage which you are talking, right, sir?
Yes,
The
right.
damage. Okay. Now, suppose you see, sir, here in this figure.
Yes, sir.
Now the capital A, capital B, capital C, it is a three different drop heights. Capital
Yes,
A, it is a 1.5 meter drop height. B is 2.3 and C is 3 meter drop height.
right, sir.
So now small A's, you can see all three figures. Small A,
Mm-hmm.
the damage means a small a, small a, capital B, small a, capital C. So this three figure means the one column, first column you see the damage intensity is increasing. Okay, the red color portion, it is
Oh,
actually damaged portion.
okay. Red
Okay,
color is the damage. Right, sir. Right.
red color is a damaged portion, and the green color which it is showing, it is just transition zone. It is
Okay.
means maybe it is a reaching their damages somewhere
Right.
0.3 means 30% damaged. The blue
Right, sir.
color is remain, it is intact. So
Okay.
that's what the first column. It is actually the tension, the compression damage that we can see. Next, come to the tension damage. Suppose the right side. right side.
Right, sir.
Right side. Let's say there's a third column, C.
Mm.
The C, if you see, it is a purely tension inside.
Okay.
So how this tension actually, tensile crack propagates longitudinally, that we have propagated, that you can see in your experiments. So
Yes.
that's what actually happening here also. When you
Okay.
have a drop height was 3 meter, you can see it's a wide cracks. So that
Wide crack.
wide crack, so you can see the increasing red color, the red color, damages that we can see increasingly. Suppose you see, sir, the last row, third figure. Okay,
Right.
the last row, third figure. I can show you. Can you see in this figure, last bottom
Yes,
right
yes.
corner?
Yes.
Bottom
Yes.
right corner.
Yes, sir.
Yes,
Yes, sir.
bottom right corner, or you can say bottom top right corner. Top
Right
right
corner.
corner.
Right.
Okay, so this is the actually damage, tension damage inside the tunnel. So that's what is this color actually indicates.
Right, sir. Right. Thank
Yeah,
you,
and
sir.
yeah, and last
Uh,
row, it is the last column. You can say the D, figure D. You can see it is a top surface of the tunnel.
Salman.
So you can see in this figure the significant, crater. It's a crater, nothing but the damages. The damage you can see significantly at the top surface. Uh, from this experiment, you can see. You can see this is the hole. The
Yes,
top,
yes.
you can see
You
the
saw.
hole, or you can say this one, the top. Can you see the second heat, right side figure, the top
Yes,
surface, there is a crater, which is equivalent to the diameter of the impactor,
right, sir.
which
Right,
is
right.
equivalent to the diameter of the impactor, that you can see in that figure.
Mm-hmm.
Diameter of the impactor, you can see. Can you see here, now the
Yes, sir.
bottom
Yes,
right
this
corner,
yellow combination
the
of
red
green
color?
and red color. Yes. Yes, I can see that, sir.
Yeah. Yes, sir. So my cursor, I think my cursor is visible.
Yes, it is visible. It is, you are just revolving around this yellow and red color.
Exactly. That red color is nothing but equivalent to the diameter of the impactor.
Okay. Great, sir. Great.
Yes, sir.
Okay. Thank you, sir, for this informative
Yes, sir.
session. And I'd like to ask our
Dr.
participants.
Senthil, there is a small query from my side also. In case we change the soil that
Yes,
is
please, sir.
acting as an overburden, what will be the effect on the impact behavior?
Hmm. Sir, you mean to say buried tunnel?
Yes.
Yeah. See, there will be very slight impact that happens, sir. Because actually that is a conservative side. Maybe first the soil will fail, then the tunnel actually. So you have to define two different steps: the interaction with the impact and the interaction with the soil. That is the first step. Then the
Mhm.
interaction between the tunnel and uh, a tunnel lining and the impactor. That is the second step. So both the steps you have to define in your abacus. Then maybe, of course, some energy will absorb by the soil during the
Yes.
interaction by the impactor, right,
Yes.
sir? So
Yes.
some energy will dissipate. That energy may be very small, because if you see the volume of the soil just below the impactor, it's a hardly 80 millimeter diameter impactor. So
Yes.
even if you see whole 150 millimeter height of the soil with a diameter of 150, sorry, diameter of 80 millimeter. So the
Mhm.
volume is very small. So those soil, kitne soil, how much energy will absorb? Only that much loss will be there in the impactor, and the remaining it will goes to a tunnel lining.
Okay.
Are you getting, sir?
Yes. I'm getting it. Okay, one more question was there, sir. You like mentioned that we are going one hit, then another hit. So, up to how many hits can we go for the analysis?
Sir, you can go up to the failure, but as soon as at one point your tunnel will fail by the impactor, okay, by the nose,
Yes.
okay. But what is happening? we have made an arrangement such a way 1 feet by 1 feet ka the plate. So when the nose actually went inside or perforated by the tunnel was perforated by the nose,
Okay.
then your base plate is trying to hit. So that is why your force is keep increasing. Multi hit may our force
Right.
is increasing because of this reasons.
Okay. Okay. So
Yeah,
you have
if
to
you
indirectly assess that failure point.
exactly, sir, exactly.
Okay. Okay, sir.
Hmm.
Thank you. Thank you very
Yeah,
much.
thank you.
Excuse me, so what would be
Yeah,
the
yes, sir.
variation in the graph?
Uh, Sir, your
So what
voice
would
is
be
a
the
little bit
variation in the
echo.
graph?
What I see.
So what would be the variation in the graph if we change the cross-sectional area to rectangular or square tunnel sections?
Of course. You see, this is a semicircular in shape. Suppose if we go for rectangle, the phenomena will change. It's like a box culvert. Am I right, sir? So it's like a inverted
Yes,
trench,
sir. Yes,
or
sir.
open trench, or you can say it's like a box culvert. So your behavior will change because there is a conch, or you can say there is a sudden change in the geometry. So the high shear stress will come into the joints. See, here it is a very smooth surface. This the cylindrical tunnels, it is a smooth surface. So such a complexity will not arise, but there the shear stress or the shear failure is very important. So in such a cases, you have to adopt a shear failure criterion in the numerical simulation. Shear
So
failure
what if we
criterion.
change to oval shapes?
Yeah, yes, you can adopt. Actually, we have different types of tunnels, oval shape also,
Yes, sir.
and whatever you are saying, the rectangular shape also. Yes, sir. And elephant leg or something. There are 4 or 5 tunnels shapes are there. It is openly
So
available if you
according
Google
to
it.
you, which type is the best structure for the mountain terrain
Sir,
or
of course, yeah, what you are
subsoil?
saying, the oval or another one shape is there. I'm not able to recollect. That would
Yes.
be good. Yeah, but the problem is what happened in my case, the fabrication of the reinforcement in the laboratory, it is very important. So what happened if you are going for oval shape, uh, I have to bend my steel reinforcement by the pressure, by the pre-stress. Okay, so then the nature of the tunnel will change. Are you getting, sir?
Yes, sir. Yes, sir.
The reinforcement when you bend, of course you have to bend with entire
Applying force.
reinforcement you have to
Yes, sir.
bend
Yes, sir.
for making the oval shape or parabola or cubic parabola shapes. So that will become that will change the Johnson Hook model. Then I have to change, and those parameters may not be valid, and I have to characterize pre-stressed reinforcement. So Johnson Hook model also will change in that case if I go for numerical simulation.
So what if we use fiber reinforcement?
Yeah, yes, you can use, sir. You
Yes, sir.
can use, see, you can use the same concrete damage plasticity model, and for a
Yes,
concrete
sir.
also experiment also you can use fiber reinforcement. See, the problem is what happened, the concrete whatever we made, it should be a workable, so that 1.2 meter height may we pour the concrete. So because inside there is a strain gauge also. So when we pour the concrete, we have to pour carefully, and also we cannot put randomly this needle vibrators, because the thickness is only 50 millimeter. So the
Sir,
needle
but
vibrator
as
also
such,
may not.
the fiber
Hmm.
reinforcement is not that much, not that much fragile that it can break down or crack down anyways.
Oh yes, yes, you can. But fiber reinforcement, how we will factory may you have to order to manufacture such a
Yes,
way,
sir.
so that
Yes,
because you cannot handle it at your lab. So
yes, sir.
industry lab it's our unka manufacturing unit itself. You ask them to bend it in these shapes, then you
Yes,
can
sir.
use it. That would be better.
So because they are not prone to corrosion, and that's why they would be better in the underground scenarios.
Yeah, yes, yes, exactly, sir, exactly. That's true. But yeah, yes, that may be next level. You can do it. That would be good.
Sure, sir.
Hmm. Thank you. All the
Thank
best.
you, sir.
Thank you, sir.
I think moreover it's very hard to like numerically model that fiber thing.
Sir, we have
No,
to
it is a
downsize the
material
procedure now.
model already available, sir. Not a problem. Material
Okay.
model numerically. See, we have fiber reinforced, models. Even the abacus have the facility for modeling the behavior of the fiber reinforcements.
Yeah.
Okay, we have.
All right.
Yes, sir.
So are there any other queries among the participants? They can unmute themselves and ask.
So some others are left.
Yeah, he was about to go to PhD Viva.
Okay.
So he dropped a message and then left.
Okay. No problem. I'll talk to you. Fine, sir.
I think, sir, there are no other queries. So
Yeah, thank you. Thank you so much for inviting me.
thank you
Sir,
very
I
much.
have one question in my mind.
Yeah.
Yes, please, sir.
Sir, while we are modeling for this type of tunnel, so do we have any option in the during the modeling that we can just go for the sustainable construction of the tunnel? Means instead of virgin material, we may utilize some other material like plastic aggregate or other aggregate or other reinforcement materials like some waste land wires and other things. So, is there any provision in those during this abacus
Sir,
or other
sir,
model?
I fully agree with you. See, we have a very limited investigation in this conventional concrete itself.
Right,
So,
sir.
if you have vast knowledge on the conventional systems, then we
Right.
can. This is because this is a benchmark.
Yes, yes, yes.
Always see, if you want to if you want to know a performance of high strength steel, you should know the benchmark of mild steel. You should,
Right, right.
because your mild steel is a benchmark material. Okay,
Mhm.
if you see, if you go to the any factory, if you go, anyone knows the mild steel, unka
Yes,
characteristics including strain and stresses, everyone knows. So
yes,
we should know first the characteristics of the mild steel, then we can develop any high strength steel or composites or epoxy based steel, anything. So that's
yes,
why
yes.
the knowledge on this particular behavior of the tunnels, especially the experiments. See, mostly we have a numerical simulation, many numerical simulations we have, but the
Right,
experiments are very very limited because of the complexity, sir.
right, sir. Right.
Hmm.
Okay, thank you, sir. Thank you.
Yeah, thank you, sir.
So okay, sir. So once again, I'd like to
I
thank you.
will recollect Sushil Dhawan, sir. Sushil Dhawan, sir, good
Yes.
evening, sir. Sir, your mic is off. Your mic is off. Sir, your mic is off. सर का माइक ऑफ है तो बोलिए सर.
Yeah. Sushil sir, we cannot hear you. You are muted actually.
Now is okay?
Yeah.
Sir,
Yes.
perfect, sir. How are you, sir?
So, I am one of the younger member of your team.
Yes, sir. I know, sir. Many conferences I've seen, even including NIT Jalandhar also, I think you came, right, sir?
Yes. I know him. He is younger to me.
Sir, thank you so much. How are you, sir? How is your health? Everything is okay?
Very good. Very good.
Yes, sir. I was so happy that I think when you got a PhD from IIT Delhi, so I think, am I right? It's a few
Yes.
years,
Yes.
4 years, 5 years, five to 6 years.
6 years back.
6 years back. That's why I know. I saw maybe the Facebook or somewhere I saw, and yes, thereafter
Then
I
now
couldn't see.
I give now. 3 days back I was invited to give lecture in Allahabad in any college to MTech and
That's
PhD
good.
students. So now I want to share my experience. So I'm
Yeah.
going to
No, that's true,
Harvard
sir. That's
also.
true, sir.
So I want to keep myself busy
That's true, sir.
in sharing knowledge.
No, that's true, sir. No, that's true. It's interesting. That's true, sir.
I mean,
And please
you
come
can
to
also
NIT
invite
Jalandhar
me.
also, sir. Yeah,
Oh,
definitely. Definitely,
Dr.
definitely.
Senthil, how are you?
Can you please give me sir? Sir, I think network issue both chal raha hai.
Right.